for basic exponential growth, they're going to give you an equation. And you'll see that in all of these. So in the first, you might need to understand how to use this. This you've seen before, but you probably saw it as the PERT formula. Do you remember the PERT formula? So the principal amount, your E, irrational number, your K is like your rate, your T is your time. So you did the PERT formula. This was, in algebra 2, the PERT formula really was mostly used if something was compounded continuously. Do you remember that? That's when we used the PERT formula. Here it's more or less used in basic exponential growth. So you won't see as much in PreCalc this. Do you remember that? Just like your basic principal, investment, or amount, 1 plus or minus your rate to the T power. That was basic, at least that's what I used for my Algebra 2 kids, for basic exponential growth or decay. So lots of times if it was a starting population and it was increasing by 3%, actually I did this. If it was increasing by 3% every 5 years, I would put the period in as 5 years. I'm not sure if you guys did that or not. And then for exponential growth, as far as like bank accounts were concerned, I'm 99% confident we all use that. But this is what they more or less use for generic exponential growth. So in this first one, it says in 1970, the U.S. population was 203.3 million. By 2003, it had grown to 294 million. Use this information to write an exponential model. So we're going to write the model first, and then we're going to use the model to answer their question. So based on the information I've been given, what could I plug in for capital A, would you say? Eden? 294 million, that's what the population had grown to. I'm just going to do it in millions, FYI. And what would you plug in for A sub 0, Joe? 203.3. E is not a variable, it's a number. What would you plug in for K? Abby? Correct, because that's what you're looking for. And what would you plug in for T? Trista? 33, right? 1970 to 2003 is 33 years. So we're going to solve this to solve for K. So what do I do first to both sides, Marissa? Good. Divide away your coefficient of 203.3. I'm going to leave it as a fraction because I'm assuming it's not going to be a nice number. Then do what? Bailey? Trying to solve for K. Correct. And then, John, what's the last step? Yep. So the natural log of that fraction divided by 33 gives me a K of, and I'll round it, I got this number. I'll do 0.011, well, I'm going to write down 0.011, but when I actually use it to do my follow-up calculation, I'm going to use that exact number, so I'm going to keep that in my calculator. So the model, and we'll stay with an A sub 0 of 203.3. My k that I'm going to write in my equation just to save space is going to be 0.011t. But I know that my real k value, so as to not cut it off. Doesn't seem like a big rounding error when you cut off 1, maybe even 2 10,000ths. Doesn't seem like a big deal, but in exponential problems it will make a big deal if you only use 0.011 versus the actual number. So then the question we're going to answer is, by which year will the U.S. population reach 315? So they're giving us a new final amount, and we're going to try to solve for how long that will take. So solving it in the same fashion I solved for k, divide by 203.3 on both sides. Take the natural log of both sides. And then divide by your k value, that 0.111786, So t will equal. And so here's how I'll use that exact answer on my calculator. I'll do the natural log of my 315 divided by 203.3. And then I'll take that answer and divide it by, I can scroll up, select it, and it will just pull that exact same number down. So 39.17 years. So that's the length of time that I have to wait. I haven't answered the question because the question says by what year. So if our initial starting year was 1970, we just need to go 39 years after that, which will put us at 2009 as our final answer. Any questions? Okay. Number 2. After 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. So use this information to help write a decay model. So we're going to write a decay model. Now, in a case like this, what do I put in for A? And we're really, in order to write our model, we really are only using that first sentence. So don't waste your time and don't read anything else yet, Olivia. So you're going to use a final amount of 50, and what are you going to use as your, right. It doesn't have to be 50 and 100. It could be 1 and 2. It could be 2 and 4. As long as your starting amount gets cut in half for your end amount, it doesn't matter. Because the first step you're going to do is divide that 100 over. And as long as you made that relationship a half, then when you divide that over, you're all going to be at the same spot. Then we're going to take the natural log of both sides. That'll get rid of my e. And we're going to divide both sides by 5715. So k equals the natural log of 0.5 divided by 5715. I get that. What do you make of that? What would you write down on your paper that k equals? Mackenzie? Okay, so you're going to keep it in scientific notation, or you can just move that over to like negative 0.0000121 and so on. But you know what I'm going to do? I'm going to keep it as this, so I don't have to worry about writing. That actually takes me less time to probably write that. Keep it in exact form. So our decay model is just like that. We don't really have an initial amount yet until the next sentence. In 1946, earthenware jars containing the Dead Sea Scrolls were found by an Arab, how do you say that word? You history buffs. Bedouin. Anybody disagree? Good, we're going with it then. Tell me if it lands anywhere. And I'll get it the next time. Oh, he's right here. Andrew, you want to take a stab at it with your pencil? Suckers are faster than flies. Was that you? Am I remembering that right? Okay. If I wasn't remembering that right, then I probably really confused everybody. Okay, so now analysis indicated that the scroll wrappings contained 76% of their original. So again, your starting can be 100, and your final amount, therefore, would only be 76% of that. 100's nice to start with because percentages are really easy when it comes to 100. And then e to the ln 0.5 over 5715 t. All right, so divide by 100, 0.76. Natural log of both sides will get rid of that e. And then how do I get t all by itself if it has a fraction in front of it? You don't divide by a fractional coefficient, you thank you, Olivia. Multiply by the reciprocal. So, it's going to look like this. The natural log of 0.76 times 5715 over the natural log of 0.5. So t equals 2,262.7 years old. I mean, I hit where he was. I don't know if I got him. I think I did, but I did. Fool me once, shame on you. Is that their quote? Fool me twice, shame on me. You didn't fool me twice. All right. So what does the actual question say? Estimate the age. Okay, so that many years old. Good? All right. This logistic growth model is totally brand new to you. And this is a generic one. This function that they give us is going to actually apply to this word problem. So this function describes the number of people who have become ill with the flu T weeks after its initial outbreak in a town with 30,000 residents. So 30,000 is the number you see in the numerator. That's what that C stood for. You don't have to memorize what all of these variables stand for, but that's where that 30,000 comes from. So the question that we're first going to answer is how many people became ill with the flu when the epidemic began? So T stands for the number of weeks after its initial outbreak, and F of T stands for the number of people who have become ill. So if you want to figure out how many people were ill at the beginning of all this, what would you do, Morgan? Well, what are you going to plug in? If they're asking you a question about how many people, are they asking you to find T, or are they asking you to find f of T? F of T, which means they must have given you T. So what number are you going to plug in for T? 0, exactly. Does that make sense? So at part A, f of 0 is 30,000 over 1 plus 20 e to the negative 1.50. And so typing that into your calculator, 30,000 divided by, make sure your denominator is all locked up in parentheses, 1 plus 20 e to the 0 power. I got 1,428.6-ish. Is that what you all got? Part B, how many people were ill by the end of the 4th week? That's f of 4. I got 20. Uh-oh. Just kidding. I got 28,582. 582.99, so I'll do 583. Anybody get anything different? Okay, and then part C, what is the limiting size of f of t? Aiden? Right, it cannot exceed 30,000. So one of the ways you could, if you didn't realize that logically, you could plug in 52 weeks. Like let this whole thing pan out for a year, and if you plugged in 52 weeks, rather than the 4 that I had, if I plugged in 52 weeks, I would get exactly 30,000. So assuming that by the end everyone would be sick. What I also want to show you on this one is just what this function looks like. 30,000 divided by 1 plus 20 to the... So when I do my window, since X is the number of weeks, I'll do the first year. And since Y is the number of people infected, and there's only 30,000 in this town, that doesn't make sense to exceed that number. And so here's your, 52 weeks was long. You're really missing the bulk of it, which is right there. So everyone pretty much gets affected pretty quickly. Let me change my window to the first 10 weeks. And you can see that the spike, everyone's like spreading. Then once everybody has it, you've had it and you're not going to get it again kind of thing. So it evens out. Okie doke. Okay, Newton's law of cooling. This you do sort of have to remember what the variables stand for, just because you've done this before. A cake removed from the oven has a temperature of 210. Where would that 210 go? Do you think? Mitch, take a guess. T sub 0, the initial temperature, good. It is left to cool in a room that has a temperature of 70. Where do you think that 70 would go, Bridget? No. Do you remember the word ambient temperature? Do you remember that? So if it's Newton's law of cooling, that's just the air temperature that this cake is going to be cooling to. Or if you put something in an oven for it to rise, that temperature is the temperature of the surrounding air. So that is actually your C. And then with this next detail, after 30 minutes, the temperature of the cake is 140. That's where your T comes in, Bridget. That's your scenario T. So that's what the temperature is after 30 minutes. That's your lowercase t for time. And then they're asking us, what is the temperature of the cake after 40 minutes? So based on the information we've been given, this kind of reminds me a little bit of inverse and direct variation. You're given a circumstance, you have to find K, which is the constant, which is kind of what has the rate wrapped up in it. And once you find that K, you can then use it to answer follow-up questions. So the first step is plugging in what we know. 140 equals 70 plus 210 minus 70 e to the k 30. Okay, so what do I do first here, Nate? Good. Sarah next. Oh, I already did that. Yep. Abby, what's next? Good. And then divide by 30. So K will equal the natural log of 0.5 over 30. So now to then use that information to answer what is the final temperature of a cake after 40 minutes. So we're looking for T now, the final temperature. C is still 70. 210 minus 70 is still going to be 140. E to the ln of 0.5 over 30. And then after 40 minutes. So we're just literally going to type that in because the capital T, the final temperature, is already by itself. So 70 plus 140 e to the ln of 0.5 over 30 times 40. So there's the temperature after 40 minutes. And then the next question, when will the temperature be 90 degrees? So we're actually in that case, round 3 of all this, we know that the final temperature is 90. We're trying to figure out how long we're going to have to wait until that happens. So we're going to be solving for T. So we're going to subtract 70 from both sides. Divide by 140. Natural log both sides. And then multiply by the reciprocal, which is 30 over the natural log of 0.5. So, just typing that in. 30 over the natural log of 0.5. And then multiply that by the natural log of 20 over 140. 84.2 minutes. Any questions? Okay? Now we flip to the back. Being able to write an appropriate function based on a model is also calculator work. It's scatter plot type work. So here's a bar graph that gives you, depending on the year, the percentage of U.S. households with TVs that have cable. So they give it to us in a bar graph, and then they just changed it to a scatter plot. So 1980, 22.6. 1985, 46.2, and so on. So on your calculator, does anybody remember how to turn on the scatter plot? No? Did you do scatter plots last year? And write lines, do regressions, linear regressions, exponential regressions, log regression. So go to stat. No. Stat plot up here in blue. Second stat plot. And they all should probably say off right now. You want to turn the first one on. And your graph does scatter plots, line graphs, histograms, box and whiskers, another box and whiskers. This one has outliers shown, this one doesn't. And I don't know what that is. Maybe a step function. Your x coordinate is what we're going to be typing into L1, list 1, and your y coordinate is what we're going to be typing into list 2. So that should all be, from that point, defaulted to the right stuff anyway. So then we're going to go to stat and edit that first option. And we're going to edit our first and second list. So get rid of L1. Now, as far as the years are concerned, let's let X be the years since 1980. It's pretty unconventional to let X just stand for the year. You guys are used to seeing years since 1980. So we have 0, 5, 10, 15, and 22 as our X coordinates. 0 years since 1980, 5, 10, 15, and 22, because the last one is 2002. And then corresponding with that, the percentage of people with cable TV, 22.6, 46.2, 59, 65.7, and 68.9. Now, I want to look at my scatter plot. So first things first, make sure you have no equations typed into your y equals. Your plot 1 should be highlighted. And then you want to set your window accordingly. Your x coordinate was your years, and we went anywhere from 0 to 22, so I'll do 0 to 25. Your y coordinate was your percentage, so I think 0 to 100 just makes sense for percentages. And then when you graph it, you should see your scatter plot. Now, this doesn't say what the appropriate function is. You have to sort of decide that based on your shape. If things are linear, then you'd use a linear regression. If things are exponential looking, generally speaking, you'd use exponential. Not exponential, quadratic. Exponential would look like that, or exponential decay would look like that. A log function parent graph looks like this. And I think this does a nice job of illustrating that. So what they want you to do here probably is a log function. So stat, calculate, and here's all your regression options. Linear, quadratic, cubic, quartic, linear again. And the way you do a log is via a natural log. They don't let you choose whatever base you want. So you'll just do an ln regression. Your x coordinate was list 1, your y coordinate was list 2. You didn't have a frequency column, and you'll just hit calculate, and we have a domain problem. Why? Any ideas? Let me go to my list again. Edit, 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 edit. If I'm doing a log regression, why is this going to give me an error? Yeah. Right, you can't take the log of 0. So maybe I should have done these years since 1979. And then my x coordinates would be 1, 6, 11, 16, and 23. Now when I go to run my regression, calculate, I will not have that problem. There it is. Now, anytime you run a regression, they're going to give you the generic format up top, and then they're going to tell you what your A's and B's or maybe C's stand for. So this is y equals, my A is 21.77. I'll just do 21.8. Plus my B is 15.2 natural log of x. Good? This only brings us up to 2002. 70% of households had cable television. What do you think that is now in 2018? Higher or lower? You do? Why might it be lower? Right. What people didn't see coming in 2002 is that people are actually getting rid of cable, right? And using Netflix or whatever. And so actually this may go back down. So if you thought that, what model might you use? Quadratic. So if I did stat, calculate, and I did a quadratic regression, I'll get a totally different formula in quadratic format. And that formula that I'm given for quadratic will give me the best for whatever those scatter plots are. Nothing is perfect, right? The more perfect is, the closer R is to, do you remember this? Do you remember what R stands for? Your correlation coefficient. The closer this R, and therefore R squared, is to 1, the more perfect your scatter plot is to that equation. Very few real data scatter plots are perfect. Okay, real life data just doesn't end up usually being perfect, but it gives you the accuracy of the model. So that was 0.995. What was the other one for ln? Oh, it's about the same, isn't it? Oh no, R squared is actually smaller there. So actually the quadratic one might be a little bit more accurate, but you wouldn't have to really compare those. Okay? Do I have time for the last one? No, I do not. If there's a question like number 6 on the homework, feel free to skip it, and we'll just start with this tomorrow. Okay?